Hey guys, this video is to help you kind of visualize what's called the washer method, and it's another volume problem. This time though, we've done a couple of videos on discs, and a disc is when you take a rectangle and you rotate it. Washer method is when you take that rectangle and you rotate it, but like, look on the screen here, you see this is the line, this pink line right here is where I'm going to rotate around. I'm leaving a gap between my rectangle and my rotation line. And when there's a gap like this, it kind of looks like the rectangle's like floating off to the side. When that rectangle goes to revolve, check out what happens. It's going to spin around, start forming this disc, but it's going to leave an empty hole in the center basically. And hence this is called the washer method. It looks like a washer basically. And there's certain situations where when we graph a function and we spin it around an axis, a hole will form in the center. So when we go to find the volume, we have to cut out that hole is basically what's going to happen. So you can see this thing kind of spinning around. I'm going to stop it right about there. And I'm going to write on the screen here. The name of this thing is called the washer method. So this is basically a washer. And essentially what it is it's a disc with a hole in the center of it. So a disc with a hole. And what we're going to do is we're going to find the volume of every single washer. And the easiest way to find the volume of a washer is to treat it like a disc problem. Be like, well, discs have radiuses. What I'm going to do is say that the radius goes from here on out. And I'm going to denote it with a big R. I'm going to call this the big radius of the entire disk. But I'm also going to notice that there's a little radius on the inside. We'll say from here to here. And I'm going to call that little r. I'm going to take the volume of the entire thing and subtract the volume of the hole. That's my plan. So the volume of the entire disk is going to be pi times the big R squared times the thickness of the entire disk. Now the thickness is the width of the rectangle, so times the width. Then I'm going to take this thing, that's the whole entire big disk, and I'm going to subtract the volume of the hole. Well, the volume of the hole is the same exact formula. It's pi r squared, but with that little radius. So pi little radius squared times the thickness. So this is the whole disk minus the hole in the center is basically what's going on here. So washer method, when would we ever need to use this formula should be kind of what you're thinking about. Well, let me show you an example of when we might actually need to use this. I'm going to switch screens here and show you a function. I'm actually going to show you two functions is what we're going to look at. So check this out. I have a graph. And you can see on the screen here, this blue top curve is, we'll call it f of x. But I also have another curve, I'm going to call this g of x on the bottom. So I actually have two different graphs kind of pieced together. And I want to take the blue region that gets caught in between the two graphs, and I want to spin it around the x-axis. So check this out. I'm going to revolve this blue region. It's going to form a shape, a solid. And I want the volume of this solid. And if you take a good look at it, watch this. I'm going to sweep through here. Normally it'd be a disc that forms, but look in the center. Do you see the hole? Do you see the gap in the middle? So if I want to find the volume of this shape, I gotta compensate and kind of take into account this hole basically. So watch this. I'm going to freeze it right around there. Let's write on this thing. So what I want to do is I want to find the volume of this entire object. Volume of this thing. The only trouble is if I use the standard disk method, I won't be dealing with what's happening in the center here, which is we have basically a hole. So to figure out the volume of this thing, new strategy. This is what I'm going to do. I'm going to use washer method. I'm going to look at it and say, well, I have these big disks. So here's my disk, but inside is a hole. So what I need to do is I need to find the big radius and the little radius. I need a big R and I need a little r. Is what I need to go looking for. Now the little r is going to be from here to here, from the center, and the big R is going to go all the way out to the end. So two different things I'm kind of looking for. So on my graph, let's see, maybe I need to switch to a different color or something here. We'll try green, see if green shows up. The big radius is when you take your rectangle on the x-axis, see here's the x-axis, and you go straight up to the top curve. That's my big R right there, that green line going up and down. So I'm going to write big R. My little r, let's do it in a different color. My little r is from the axis, but it's only up to the first curve. There is my little r. So you can tell that there's two different things going on here. The big R comes from, let's see, switching colors again, comes from this f of x right here. That's where it lands. And the little r comes from this function called g of x. So this is getting pretty messy on the screen here, so I'm going to kind of wipe this out and start over here. I'm going to write that big R comes from the top function f of x, and little r comes from the lower function, we're calling it g of x. If you're having a hard time seeing what I'm talking about, f of x is this top blue curve, and g of x is this one right here. And you can see, if you look, you can see how g of x scoops up in the bottom there. So what I'm going to do is I'm going to set up the washer method, and I'm going to say that volume equals adding up a whole bunch of infinitely many washers, just like we do with the disk method. So I'm going to have an integral from a to b, and it's going to be pi times the big radius squared minus pi times the little radius squared. So I'm going to pull the pi out in front, and I'm going to do big R squared minus the little r squared, and then times it all by the thickness, which we're going to call delta x. The thickness is going to be infinitely small on these things. So big R and little r, we were just talking about what they are. It's f of x and g of x. So usually when I write this, I'm going to erase these. Big R squared minus little r squared. What I'm probably going to really write it as is f of x squared minus g of x squared. The f function minus the g function squared. And it's top minus the bottom, basically is how you want to think about it. And that's my general setup. So washer method, to kind of recap here a little bit, washer method is helpful for when we have a solid formed by two functions, not just an f of x, but we have f and g. And when it spins, a hole is created in the center. So I'm going to write washer method is for holes, is for when a hole is formed. Which happens more often than not, actually. So when we spin a rectangle around a curve and we end up forming this gap. Now the rectangle, the slice that we always talk about when we're doing the disk method, it's in this picture. I don't know how well you can see it, but it's right here. Let's see if we can kind of shade that in. That's my rectangle. Notice it's up above the x-axis a little bit, and it's caught in between f and g. It's caught in the middle, and then it's spinning around and forming a gap. So that's why we need this formula for washer method. So I'm going to post a couple videos about this. We're going to practice it in class, and hopefully it helps. I'll be coming out with some more videos soon.